efficiency as a law, cosmic minimalism, and the energy ledger. If observation is information flow, then there's a price list taped to the back of reality. The universe is thrifty. It spends only when it must, and it compresses whenever it can get away with it. Start with entropy and the way we actually describe systems. We don't track every molecule in a room. We use temperature and pressure. That's coarse graining, keeping the variables that matter for outcomes, discarding the microscopic clutter. And here's the kicker. The macroscopic laws we trust, like thermodynamics, emerge because so many microstates map to the same macrostate. Efficient descriptions win because the world doesn't need the rest for predictions at our scale. Now bring in Landauer's principle, the bookkeeper's favorite line. Erasing one bit of information costs at least kT ln2 of energy dissipated as heat. It's not a metaphor, it's a measured bound. A memory reset in a computer dumps heat. A demon trying to cheat the second law pays his tab at the eraser. Translate that. Information isn't free. Losing track on purpose, resetting, compressing, overwriting, has an energy toll. Any rendering scheme that creates, stores, or clears bits is pinned to physics. What about the universe itself? There's an eerie hint in the holographic principle. Black hole thermodynamics tells us the entropy, the number of possible internal configurations, scales with the area of the horizon, not the volume inside. 1/4 of the area in Planck units gives you the bit count. That's so strange it sounds like a parable. The boundary knows more than the bulk. In lab-grade theory, add SCFT makes that literal. A gravitational world in the volume is exactly encoded by a quantum theory on the boundary. Our universe isn't de Sitter, so we can't copy-paste, but the pattern is loud. Count bits on surfaces, not in volumes. If bits scale as area, full resolution everywhere becomes absurdly expensive. You don't store every voxel's microstate in explicit detail. You keep boundary data and let bulk behavior be an emergent, efficient consequence. That's compression. Not sloppy, not lossy in the predictive sense, but minimal. The state you need is only as detailed as the questions you can physically ask. Here's an analogy with teeth. In software, lazy loading fetches assets when a player walks into a region. In physics, sparsity and symmetries cut the cost. Fields are smooth over scales, interactions have ranges, correlations fall off with distance, gauge redundancies hide wasted description. You never paid for every pixel. You paid for modes that carried energy and information across your horizon. Everything else stayed on the shelf as potential, not instantiated bookkeeping. Bring back Landauer and ask about the ledger at cosmic scale. Every time information is irreversibly recorded, when decoherent spreads and alternatives can't re-interfere, you've effectively allocated bits to classical history. You can't unspend that without a matching energy cost. Erasing is heat, storing is entropy. The universe chooses to let most details wash out, keeping only robust, redundant records, multiple photons bouncing off a chair, many molecules carrying the same trace. Redundancy sounds wasteful, but it's how facts become objective. Many witnesses, same story. Now stack this with the horizon. If the maximum number of bits inside your patch scales with its boundary area, then there's a hard ceiling on how much distinct detail can be physically present and retrievable within your worldline. You're living in an instance with a storage budget written on its edge. Try to imagine full fidelity everywhere, all at once, and you run straight into the bound. There's another efficiency play hiding in entropy and coarse graining, effective theories. You don't simulate quarks to model airflow over a wing. You use Navier-Stokes within a domain of validity. The cosmos does the same. Long wavelength modes govern structure growth. Short wavelength noise averages out. Inflation stretched quantum jitters to cosmological scales, but even then, only specific combinations survived to the microwave sky. The rest got smoothed, packed into parameters, compressed into a handful of numbers. Spectral index, amplitude, baryon density. Minimal inputs, maximal reach. Here's a micro story. A team running a galaxy formation simulation fights memory limits. They can't resolve every star, so they build subgrid models, rules that stand in for unresolved physics. Feedback from supernovae isn't simulated per blast. It's injected as heat and momentum according to calibrated laws. Critics grumble. Then the results match observations better than brute force versions did. The lesson lands. The right compression preserves what matters. But there's a cost to every shortcut, and physics forces honesty. Landauer says you pay to forget. Holography says you store on the edge. Thermodynamics says high-entropy states are typical, so order must be local, engineered by gradients and flows. If a rendering metaphor helps, use it like this. The universe instantiates only the correlations that can be accessed and preserved within horizons, encodes them redundantly for stability, and lets the rest remain implicit in symmetries and constraints. Not hidden by a programmer, but unnecessary to the questions any observer can physically pose. Hold that ledger in mind. Efficiency isn't an aesthetic, it's a survival trait baked into the laws. And just when we thought the budget was comfortable, a new telescope stared deeper and the timelines got tight. The early light that shouldn't exist, JWST's galaxy surprise. Then JWST opened its eye and the early universe looked crowded. Within months, preprints lit up with candidates at redshifts 10, 12, even beyond. Translation: we were seeing galaxies as they were a few 100 million years after the Big Bang, and some of them looked mature. Too bright, too massive, too structured for their age. Timelines we'd sketched with comfortable margins suddenly felt tight. Here's why that matters. Our standard model of cosmology, lambdictum, lays out a growth plan. Tiny fluctuations seeded during inflation grow under gravity. Dark matter collapses first, making halos. Gas falls in, cools, forms stars. Feedback from supernovae and black holes regulates growth. The result is galaxies that assemble over billions of years. At redshift 10, you expect small, clumpy blue systems with modest stellar masses. JWST's early photometry hinted at objects with stellar masses of 1 billion suns or more and star formation rates that implied rapid assembly. If true, that compresses the schedule. Before you yell broken model, take a breath. First look photometry is slippery. You're fitting spectral energy distributions with only a handful of filters. Bomber breaks can masquerade as high redshift. Dust can redden a lower redshift galaxy into looking distant. Emission lines can boost brightness in ways templates miss. Teams race to secure spectroscopic redshifts, clean fingerprints from features like Lyman alpha breaks to confirm distances. Some candidates slid down in redshift with better data, others held fast. The picture got messier, not simpler. Meanwhile, simulators started sweating. If even a fraction of those early massive candidates were real, star formation had to be more efficient in dense, pristine environments than we'd baked in. Metal-free gas cools differently. Fragmentation can be wild. Massive stars form quickly, die quickly, and pour energy back into the gas. Black holes might seed earlier or accrete faster. Feedback recipes tuned on later epochs might not port cleanly to the first few 100 million years. Subgrid models, our compression tricks, needed new terms. There was also an instrument twist. JWST's NIRCam sees with exquisite sensitivity and resolution, but the early universe is small on the sky and faint per surface area. Surface brightness dimming is brutal. Something stretched by redshift loses brightness as 1 plus Z4. Yet some early candidates looked surprisingly large in angular size for their redshift, or packed more light per area than expected. That raised eyebrows. Were we biasing our samples by picking the brightest outliers? Were we lensed by foreground structures more often than we realized? Gravitational lensing can magnify and stretch distant galaxies, making the exceptional seem common if you don't account for it carefully. As spectroscopic follow-up improves, several masses and sizes continue to move toward more conservative values within lambdictum allowances. Here's a micro-story. A small team working nights in a windowless room pushes through stacked exposures from a deep field. The pi bets a good bottle of wine that their brightest object will drop to Z tilde 5 once they get spectra. The postdoc smiles, shrugs, and says, "I hope you like cheap Merlot." Weeks later, the spectrum comes in. The break is clean. The absorption sits where early hydrogen should sit. The object stays at high redshift, though its inferred mass ticks down after better modeling. The lab cheers, then groans. Their toy universe just got more complicated. What does this have to do with rendering and efficiency? Think in budgets. The universe doesn't get to violate causality or energy bookkeeping to fill in detail we find surprising. If early galaxies are more common or more evolved than our priors assumed, there are only a few levers to pull that respect the ledger. You can push star formation efficiency up in dense halos. You can alter the initial mass function so more massive stars form early, front-loading light. You can tweak feedback couplings so gas turns into stars before winds quench it. Or you can acknowledge selection effects. We're preferentially seeing the luminous tail because those are the ones we can see. There's also the possibility that our cosmological parameters shift within allowed uncertainties. The matter-power spectrum's tilt, the amplitude sigma 8, the baryon fraction, nudge those and small-scale structure grows a bit faster. Not a cheat, just a retune within error bars as datasets update. That said, the core lambdictum scaffolding has survived rough tests. The cosmic microwave background's acoustic peaks, baryon acoustic oscillations, lensing maps, and primordial abundance measurements. You don't throw that away because early snapshots surprised us. You integrate the surprise. Here's where the rendering metaphor holds its weight without overreaching. JWST doesn't force the universe to invent galaxies to satisfy a camera. It exposes where our compression, our assumptions, was too aggressive. We'd summarized complex early gas physics into a few parameters. The data said not enough. So we spend more bits, more detailed models of cooling, starbursts in metal-poor gas, early black hole growth, radiative feedback in clumpy media. The map didn't glitch, our subgrid did. One more tension to park for later. A few early candidates showed odd sizes and surface brightness profiles that didn't line up cleanly with simple exponential disks or spheroids at that age. Some of that will wash out with better deblending and lens models. Some of it might point to early mergers shaping structure fast, and some of it might be a reminder that what we call galaxy at Z12 isn't the same creature as at Z1. Names compress. Nature resists, and follow-up will sort genuine outliers from selection biases. The stakes remain sharp. If the early timeline is tighter, then our efficiency story isn't optional, it's required. The universe had to build complexity quickly using minimal inputs and hard constraints. That's not sloppy rendering. That's a system leaning on symmetries, fast channels, and redundancy to stabilize facts early. We'll carry that forward as we step into places where the universe looks empty, voids and cold spots, and ask whether absence is a flaw or the cleanest kind of compression. Voids, cold spots, and missing texture packs. Elsewhere, the sky looks like someone forgot to paint. You swing the camera to the Boötes void, a region hundreds of millions of light years across with almost nothing in it, and your first thought is, under-rendered. A missing texture pack. But get this straight, emptiness doesn't mean error. It can be exactly what you expect when initial conditions ripple forward. Start with the cosmic web. From tiny quantum jitters stretched by inflation, gravity amplified slight overdensities into filaments and nodes, and it evacuated the spaces in between. Matter flows out of shallow valleys toward growing peaks, and the carved-out regions puff into voids. The biggest voids, like Boötes, are rare but statistically allowed in lambdictum. You run enough realizations of the initial power spectrum, and a few huge hollows pop up. They look like gaps in a painting because our eyes love uniform coverage. Nature prefers contrast. Here's a micro story. A survey team plots galaxy redshifts in a wedge of sky and watches the dots thin out, then nearly vanish. Someone jokes the instrument died mid-scan. The instrument's fine. The universe just left that volume empty. A few lonely galaxies haunt the interior, Most cling to the walls the way lights at night trace a city's highways while farmland sleeps dark between them. Under-rendered? No. Rendered as absence. Then there's the cold spot in the cosmic microwave background, a patch a few degrees wide that's noticeably cooler than average. The CMB is our oldest light, coming from when the universe cooled enough for electrons and protons to bond and photons to travel freely, about 380,000 years after the Big Bang. Across the sky, tiny temperature variations map density ripples. The cold spot is odd because it's big and deep. Some argue it's just a statistical fluke, a tail-end lump in a Gaussian field. Others point to the integrated Sachs-Wolf effect. As photons cross large evolving structures, they can gain or lose energy. A giant supervoid along our line of sight could leave a cooler imprint. Surveys did find an extended underdensity in that direction, but whether it's enough to cause the whole dip is still debated. Current analyses leave room for a modest anomaly without overturning Gaussian initial conditions. Notice what's happening to our metaphor. A missing texture implies a bug, a place the engine forgot to fill. But the physics explanation says emptiness can be a feature. Voids aren't just holes, they're laboratories. Galaxies inside them evolve with fewer interactions, less harassment, quieter inflows. The rules of the game are the same. The starting conditions are different. Compression would favor emptiness where correlations don't need to be stored because there's nothing to correlate. A blank region costs fewer bits. Stakes matter here. If you're hunting for breaks in the code, anomalies are tempting. You want the smoking gun, the glitch that says simulated. But you can fool yourself if you don't weigh probabilities right. In a universe this large, the far tails of distributions will show up somewhere. Rare isn't impossible. When you see a supervoid or a cold patch, the first question is who forgot to render. It's how often should this occur if the model is true? If the answer is occasionally, you take a breath and keep going. There's an irony worth sitting with. Voids carry less information than crowded nodes. If the holographic whisper is right, that boundaries count. The empty interior doesn't demand storage. What needs encoding are the walls, the filaments, the patterns at the edges. That's boundary-driven economy. You don't waste bits detailing uniform nothing. You spend where gradients live, where signals can propagate and be measured. In that sense, the cosmic web looks like a smart compression, sharp where it matters, smooth where it doesn't. At the same time, the cold spot forces discipline. If it's beyond what inflationary statistics allow, then something about the initial save file needs revision. Maybe inflation wasn't perfectly simple. Maybe there were features in the potential or relics from pre-inflation physics. Or, yes, maybe a giant late-time structure stacked along our line of sight is doing more work than we thought. Distinguish anomaly from expectation without hyping either. That's how you keep trust with a sky that doesn't owe you clarity. Here's another micro-story. A graduate student builds mock skies, injecting fake voids into simulated large-scale structure and ray-tracing CMB photons across them. She tweaks profiles, depth, sizes, and watches the temperature imprint shift by microkelvins. The numbers drift toward but don't quite reach the observed cold spot. She sends the plot to her advisor. Close, not enough. The reply comes back. Good. That means we're measuring. And this loops us back to boundaries. Voids, cold patches, filaments, they all speak in the language of light. Photons ferry the evidence. If nothing outruns light, then the shape of emptiness is set by what light can cross and what it can't. Where signals can't go, nothing can be asked. Where signals skim edges, boundaries matter most. Under-rendering isn't the right frame. Latency is. If you can't send the request, you can't expect an answer. Which is why, to see how far that rule goes, we have to follow light to its speed limit. Latency of reality, the speed of light as a hard cap. While that debate over void simmers, the real arbiter of what can be asked and answered is speed, specifically, the speed of light. C isn't just a number, it's a contract. It caps how fast information moves, which means it caps how quickly reality can coordinate itself across distance. If you think in render terms, C is your maximum frame sync rate for the universe. Start local. Your light cone is the set of events you can influence or be influenced by. Draw a point for you, then a cone opening forward in time for what you can touch, and a cone opening backward for what could have touched you. Anything outside those cones is off-limits. Not later, not with better tech. Off-limits in principle. That's latency baked into geometry. Space and time mix so that any path trying to outrun light gets pushed outside the cones and loses causal contact. Now scale up. Expansion stretches the grid itself. Galaxies don't rocket away through space faster than light. The distances between comoving markers grow. That's why recessional speeds can exceed c without breaking the rule. You still can't send a message faster than light to catch a fleeing galaxy if the expansion between you grows too fast. The metric gives you horizons because even a photon sprinting at c through the local fabric can't make headway against the global stretch.